Today I'm going to show you how to build this Arduino based power and energy meter. And so what we're going to do is we've got a regular Arduino here, and we're going to use a voltage divider and a current sensor, and we're going to be able to measure positive and negative power and energy. And here we have energy in the negative direction because I'm charging this battery right here from my other batteries. I've got one battery charging another battery. And if we plug a power supply into the big battery, so now we have a power supply going in, and now you can see that we have a net power of 4 watts going into the battery when before we were drawing, and so now you can see that the power and the amps are now positive. And so it works in 2 directions, and it's a lot of fun. So today is the prototyping day where I'm going to do this all on a breadboard and show you how it works, and in a future video we'll hook it up into a real application. So here's the schematic we're looking at. I used a 12-volt battery, and we're going to power the positive and negative buses here. And then we have our Arduino. And then here is our OLED display. We have ground going to ground, and the VCC here is the 5-volt port on the Arduino. And then we have the SCL and the SCD. And the SCL goes to port 5 and the SCD goes to number 4. Now the current sensor, we have here, this is the load side, and so over here I just put in a light as a load, but all of your loads go through the current sensor, and they start from the positive, they go through the current sensor, and then they go on to ground. Now the connection, this takes a 5-volt power supply, so we're going to hook up to the 5-volt power supply on our Arduino. And then the purple wire is going to go to analog pin A0. Now I couldn't find the voltage sensor board, but basically it's a voltage divider. And so we got 2 resistors here, and they have both, on this side they both go to ground, even though one is labeled differently than the other. And then the sensor output right here in the middle, that goes, the white wire goes to analog input 1. Now in order to measure current, you've got a couple of choices. You can do a shunt resistor or a Hall effect sensor, and in this case I'm going to use the Hall effect sensor right here. And basically this works where it has a 5-volt power supply, which is this red wire right here coming from the Arduino, a ground, and then this purple wire is the output, and it outputs between 0 and 5 volts. So here's how I have it hooked up. I have all of the wires from the negative that would have gone to the battery on one side, and then I have a single wire going to the battery right here. So that collects all of the current that is going to the battery through the Hall effect sensor. Now, from the Hall effect sensor, we have this setup right here. So here is my Arduino, and I have a positive and negative bus up here, and then I've duplicated it down here, and the positive and negative comes from the positive and negative on the battery itself. So this is between 11.5 and 14.6 volts. Now we go into the Arduino. So the VIN right here and the ground, and then the red wire right here, that is going to be our 5-volt power supply. Now that 5-volt power supply does 2 things. One thing, it supplies power to the Hall effect sensor and also to the OLED display right here, the red wire that you see. So the OLED has a power supply, a ground, and then 2 data connections. And those data connections are up here on A4 and A5. Now the purple wire from the Hall effect sensor goes into analog input 0. And then you'll see a white wire that I have here into analog 1, and that will be for a voltage that I will hook up in a few minutes. But right now what I'm doing is I want to measure current. So it's a very simple circuit, and then what I'll do is we'll go into the sketch and I'll show you how this works. All right, let's take a look at the ACS 712 spec sheet. Right down here under the selection guide, you see we have 3 versions. There's the 30 amp, the 20 amp, and the 5 amp, and that's indicated by these numbers here. What you need to understand here is that they have a conversion factor of how many millivolts per amp they output. And so I bought the 20 amp version, which means it has 100 millivolts per amp. And so we're going to use this data in our sketch to calculate the actual current through the current sensor. All right, now let's take a look at this sensor. So how this works is this. If we graph the output voltage, we want to measure current going in the positive direction and the negative direction. And if we had it right here at 0, so if this is current as a function of voltage, if we had it all here, it would look something like this because we couldn't measure any negative current. So what they did with this chip is that they offset it in the positive direction. So here we're gonna measure current as a function of voltage, and if our supply voltage is 5 volts, and that's called the reference voltage, then the 0 point is going to be 1/2. So this is 2.5 volts, and here is 5 volts. And that offsets it, so that means that we can measure positive and negative current like this. And so anything above 2.5 will be positive, and anything below 2.5 all the way to 0 will be negative. And so the voltage, if we had 2.5 volts, then that means that the current I is 0. And this is really handy because now we can do quite a bit with this sensor, all within a 5 volt range. Now we have a conversion, we have 100 millivolts per amp. And this is for the 20 amp chip that I bought. And so now we can use all of this to precisely calculate the current at any time. So let's take a measurement here. I'm currently, I'm measuring 20.6 watts and a current of 1.59 amps. That's what the meter is reading. That's what my circuit is reading. Let's see if this works. I'm going to measure. I don't have a second camera. The voltage at the sensor is 2.65, and the ADC is reading 542. Okay, let's see if we can figure this out. So we have 542 times 5 divided by 1024. Let's see what this is. .65. Okay, so that voltage works, and how we figured that out is that we have a resolution of 1024 over 5 volts, and that's because this is how the Arduino can read an analog input of 542. So this makes sense. All right, now the next thing is that we need to convert this voltage that we read and convert it into amps. So we'll take 2.65 minus 2.5. So 2.65 and 2.5, and that's going to be 0.15 volts. And this is going to be in the positive direction because I'm currently charging. Now, to calculate current, and that's going to be 0.15 volts. And then we're going to say that we have 1 amp for 0.1 volts. So this is 100 millivolts. So that means we say 0.15 and 0.1 divide, and that's going to equal 1.5 amps in the positive direction. And what did we measure? 1.6. And so there's a little bit off on what this is reading because the voltage is fluctuating slightly, so I'm taking a sample, and my sample doesn't exactly match what I just read from the meter, but that's because this meter did it at an instant, at a point in time that is not exactly what I read from my meter. So this all makes sense, and this works. So let's see how we can do this in the sketch and come up with this math right here. So here is the Arduino sketch. First thing we're going to do is include the libraries that we need, and we set some definitions for the OLED display. And I'll have this code available to you, so you don't need to try and write it down. But these are required in order to run the various processes that we're going to discuss. So as I just mentioned, we have 3 scale factors depending on what size of sensor you bought. You have a 5 amp, the 20 amp, and the 30 amp. And we are at 0.1 volts per amp or 100 millivolts per amp. And we'll use this a little bit later. So we define what those are, and then we define the variable types that we need. So we have the current sensor voltage, the current, power, energy, and I have named here what's called a 2-second energy. I will explain that in a few minutes. And we have the 0 point that I just discussed, which is 1/2 the V reference. And so I just typed it in manually because I'm using the 5-volt reference on the Arduino. We have the current sensor value. This is going to be what we're going to read from the analog to digital converter. And then we are going to cycle over a certain number of times for precision, and I just put in 1,000 so that as a placeholder we could change that at any time. And then we have a couple other battery voltage and elapsed time. Now we don't have to use the serial monitor, but I go ahead and put it in the setup unless I need it. And this is information you need for the OLED display, the address, the contrast, and then we clear it. And here we need to define how we're going to measure the reference voltage. Now I'm using default. You do not need this line, but I just put it in for clarity. You could use an internal or an external reference, and I have those commented out. If you use the internal, that would go from 0 to 1.1, but we don't need that. I'm just going to use the 5-volt reference. So here's some more code to initiate the display. I'm going to set the text size, and then here we're going to read the values of the analog input for the current. So the cycle count up there, you can change it to anything you want. If you look online, a lot of people are doing anywhere from 500 to 1,000 for precision. It's not a good idea to just take a single sample because the first one is a known issue that it will be bad, and so we're just going to do it over 1,000. So here we're going to read the current sensor value is going to be the analog input from A0. And then here is the math that I just showed you, which was the current sensor value times 5 volts divided by 124. That will be the voltage, and then we're going to add it to the previous one that we did in the loop. And so when we get it all done, then we need to divide here by the cycle count to get the actual battery voltage. Or I'm sorry, the current sensor. Here is the battery voltage that I also have, but that white wire that I have here, this is the white wire. I don't have that hooked up yet, so we'll be doing that a little bit later. So when you subtract this all out, or you divide by 1,000, that gets you the future battery voltage that we'll do in a minute and the current. Now, as I mentioned before and showed you in the calculations, we need this current sensor voltage, and we subtract it from the 0 point and divide it by the scale factor to calculate the actual current. Now, for right now, for the power calculation, I need a voltage, and I know it's about 13, so I just put a little debug line here, and I'm going to manually input the battery voltage at 13 for the first part of the test. So the power is the battery voltage times the current, and so that's going to be how you calculate that. And then what we have here is I have an elapsed time function is that, see, I'm going to delay 1 millisecond here, and then I'm going to delay 999 milliseconds, so that's a full second. And as you can see here that I have that a 2-second delay plus elapsed time, and that's because down here, after we show the results, we want to delay a second before we clear the display and start the next loop. So that's 1 second here, 1 second here, so the total elapsed time is 2 seconds. So when the first time it goes through, what we want to do is that we don't have any elapsed time, then there is 2 seconds, and we add it to the previous elapsed time. And we need this in order to calculate energy. So I've defined a variable called the 2-second energy, which is the current times the 2 seconds divided by 3,600 seconds per hour. So this will give us in amp hour. So this 2-second energy, what we're going to do is we're going to take that 2-second energy and add it to the previous energy to have the total energy as it loops over and over and over. And this will show in amp hours. And then we want to display the value. I find it a lot easier to work with OLED displays than the serial monitor because I can just unplug it and read it. And the only way that you can get the serial monitor to work is if your computer is plugged to it at all times, and that makes it difficult for me. So we output the data, and so here I have the first thing is I want to know the raw sensor value, and this is going to be an analog to digital converter anywhere from 0 to 1024, which I just showed you. And then the battery voltage, currently I'm going to show the CAN 13, but we will change this in a minute, the current, the power. And then for debugging purposes, I want to show to 4 decimal points this 2-second energy and the total energy in amp hours. And then when it just does all of this, it goes back through the loop, takes another sample over 1 second, and runs the calculation again. I just realized that this elapsed time, I was doing this for debugging because I was manually calculating to make sure that it was counting correctly. And so in the final version that I post, we won't have this because this was just for debugging. All right, so what I have here is I have an alligator clip going to a 12 volt adapter, and then I have an inverter right here. And then I've got a load, and this will charge a battery. And so I'm going to show you how this works. So right now the battery's not connected, so we'll go ahead and I'll plug this in. All right, so we plug that in, and now the inverter is on and it's in idle mode. And so from the negative lead of the inverter, we're going through my ammeter. And so we're reading 0.23 amps. All right, now we'll go back through here and take a look at what this is showing. We're showing current in the negative direction of 0.22 amps, which is very close to what I just read. And the power that I've calculated is based on a 13 volts that I've manually put in there, as I mentioned before, but that's about 2 watts. And then you will see the energy, the total energy. This is because I was charging it all night long, but I'll show you how that works in just a second. And then you can calculate that 509 raw sensor value and convert that to voltage and then the amps as I did on a piece of paper. So now here is my battery, and then here's the cable. Plug that in right here. All right, now we've gone up to 1.2 amps on the meter, and let's check and see how accurate this is. 1.21, very, very close. So I'm really happy with the accuracy of this, and it works great. And so, as I mentioned before, this measures energy going out of the battery and into the battery. Now, currently this meter is only showing from the inverter. So let's go ahead and disconnect the inverter, and then I will show you how that works in the positive. Okay, so we've disconnected the inverter. Our current has gone down to 0. This will not be quite 0. This is showing a current of 0.03 amps, and this is due to a slight inaccuracy with the reference voltage. And if that is something that is going to be a problem for you, then you're going to have to use a more precise reference voltage. but it's very, very small and negligible as far as I'm concerned. So now I have another power supply right here, and this is going to be, I'm going to plug it in here, and this is a lead that I have that goes in through the Hall effect sensor. So let's plug that in. Okay, that's plugged in, and now we don't have anything through here because that's only measuring the inverter. But let's go over here and take a look. Now we have current of 1.5 amps, and we have a positive power of about 20 watts. So if you look at the transformer for that charger, that's very, very close. And then you can see here that this 2-second energy is 0.0009 amp hours, and if we multiply that by the elapsed time, then we can get the total energy. And so I let it run all night long, and it added up very accurately, and it was really handy. I'm very impressed with how it works. And so that's how that works. And so what I'm going to do next is that I'm going to make this just a little bit less demo-y, and then I'm going to hook it up to my telescope and test it. I'm not sure if I have that on this video or not, but that's the next step, and then I'll make a nice case for this. Okay, at this point we're ready to get the voltage measurement of the battery itself. So I've defined a few more variables. We have the sensor value, and I've defined it as a float so that the math will work correctly in C instead of an integer. And this is going to be the input value of A1. And then we're going to calculate the battery sensor voltage. And then eventually we're going to calculate the voltage itself. And it's done by two precision resistors, R1 of 30,000 ohms and R2 of 7,500 ohms. Now, just like before, in the cycle count, we're going to analyze the battery voltage a number of cycle count times, and then when we're done, we're going to divide by the cycle count in order to get the final battery voltage. So we're going to read from analog A1, and this is the white wire. This will be our battery sensor value. And we're going to calculate that voltage as that value times 5, which is from 0 to 5 volts on our analog input divided by the resolution of 1024. Now the battery voltage itself is if we take this battery sensor voltage value divided by R2 divided by R1 plus R2, and then we're going to add that to the previous battery voltage that we read in the loop. And so that will increase every time, and then we've calculated our final voltage by divided by the cycle count. And then I have commented out this debugging where I had 13 volts during testing, and then we'll have the actual output down at the bottom. Okay, the first thing we want to do is measure the actual battery voltage, 13.55 volts. So now I've connected the white wire here from the sensor value into the A1 analog input right there. And now we have the real-time voltage, 13.55 volt, and it is an exact match, or at least within 100th. And that is great news. So now the power output is going to be accurate. Before I was just estimated. So we have 21.49 watts, and we're charging. All right, that's it for today. Stay tuned for next time. I'm going to put this up and test it and see just how much my astrophotography rig is actually using over time. And this will be answer a question I've had for some time. So I'll see you next time.